we are discussing about Krylov subspace methods for solving matrix equations iteratively. So, today we will discuss about conjugate gradient method, which is very first Krylov subspace method for solving symmetric matrix equations. The classes before we have discussed about Arnoldi's method, through which using something like a modified Gramschmidt method we can get orthogonal basis for Krylov subspace, and then we have also seen how to apply this for solving matrix equation using full orthogonal method or FOM, and we also looked about different variants of FOM and then further looked into Langso's algorithm, in which FOM can be converted for symmetric matrix equation, which essentially gives something like a tridiagonal matrix system, in which direct solution like TDMA algorithm type algorithm can be utilized for faster solution. And now we will continue this discussion for conjugate gradient method. Before going into that, I will again quickly review few of the important things in Krylov subspace method as well as full orthogonal method and Arnoldi's method, which will give a base for continuing this discussion to conjugate gradient method. So, if we look into the matrix solver solution equations, for example, when we discussed about steepest descent algorithm, which is the building block of any projection method, and Krylov subspace method is also just an extension of general projection method, where the projection space is not one dimensional, rather multidimensional. So, if we look into the steepest descent algorithm, for example, we have a function, we have to solve A x is equal to b, and we define a function j is equal to x transpose A x minus x transpose b, which has to be minimized. J mean will imply A x star is equal to b. This has to be solved. So, we get the exact solution of A x is equal to b. So, we start with the isocontours of j, and this is basically steepest descent what I am discussing here. So, these are the j constant lines, or we call them j isocontours. These are the lines over which j is constant. So, we will start from any value x 0 and evaluate what is b minus A x 0, that is equal to r 0, and then I will move along r 0. I will keep on moving along r 0 till just one second, the r 0 has to be orthogonal to it. So, let us select the x 0 here. This is just for convenience of explaining that this x 0 here, and I will keep on moving along r 0, say up to a distance alpha 1. Here the r 0 vector will be tangential to the new isocontour, and I have to change the such direction. I have to evaluate. So, this is x 1 where x 1 is equal to x 0 plus alpha 1 r 0, for example, and I will evaluate r 1 is equal to b minus A x 1, and then I will move along r 1 to find out x 2, where x 2 is equal to I can probably write x 2 is equal to b minus x 2 is equal to x 1 plus alpha 2 r 1, something like that. So, at each step x will be updated as a function as x k plus 1 is equal to x k plus alpha k plus 1 r k, something like this, and my r k will be defined as b minus A x k. So, now if we look into this update into little detail, or just work out the updates for first 2-3 steps. So, I rather let us erase this. I keep with the relations that x k plus 1 is equal to x k plus alpha k plus 1 r k, and r k is equal to b minus a x k. Exactly this is what we have done in steepest descent, which is building block of projection method. So, this later will give us what are the general projection methods. Now, I can write that let us use another pen. X 1 is equal to x 0 plus alpha 1 r 0. Then x 2 will be x 1 plus alpha 2 r 1. Now, what is x 1? X 1 is nothing but x 0 plus alpha 1 r 0. And what is r 1? R 0 is equal to b minus a x 0. R 1 is equal to b minus a x 1 is equal to b minus a into x 0 plus alpha 1 r 0, which is b minus a x 0 is r 0 minus alpha 1 a r 0. So, I can substitute here that x 1 is x 0 plus alpha r 0, and this is plus alpha 2 into r 0 minus alpha 1 a r 0. So, this is x 0 plus alpha 1 plus alpha 2 r 0 plus minus alpha 1 alpha 2 a r 0. Now, can we see that this can be written as also x 0 plus say a 1 r 0 plus a 2 a r 0. Similarly, if I write expression for x 3, this will be x 2 plus alpha 3 r 2, and now I will substitute, calculate the values of r 2 and x 2 and substitute it here. I will again get x 0 plus a say b 1 r 0 plus b 2 a r 0 plus b 3 a square r 0, so on. So, I will get a general expression for mth order or mth iteration of x as let me wipe this part out, so that or let me write down the general expression that x m after mth iteration is equal to x 0 plus say theta 1 r 0 plus theta 2 a r 0 plus, and it goes up to theta m plus 1 a to the power x 3 is related with beta 3. So, theta rather theta 3 a to the power m minus 1 r 0. So, the entire update of x 0 becomes a function of r 0 plus a r 0 plus a to the power m minus 1 r 0, and precisely that gives us the idea of Krylov subspace, that x will be updated in a affine space, so that x m is equal to x 0, x m is equal to x 0 plus k Krylov subspace of a and r 0, where k m a r 0 is the space spanned by span of r 0 a r 0 a square r 0, so on a to the power m minus 1 r 0. So, this is what is the basic definition of Krylov subspace, what we have used earlier. So, now if we look into the into the definition how x is updated, and when updating x, for example, when we looked into steepest descent, x is always updated along r, and in that way we made it also a point that the new residual vector r should be orthogonal to the previous residual vector or also to the functional subspace isocontour of J. So, there is a constraint on how x will be updated and based on which the values of alpha are calculated. So, x is anyway updated in this particular plane, which is space or which is Krylov subspace. This is the Krylov subspace. X is always updated in on Krylov subspace. And what are the coefficients through which these updates will be there? What will be theta 1, theta 2, theta m? That will come from the projection constant that the update should be orthogonal to, or the residual should be orthogonal to a particular plane. So, if we now look into the recap what we have seen in Krylov subspace, which is will also write that this is a general projection method. And we have also seen that this update is updating x in Krylov subspace will make it convergent to the exact solution x star, and the residual, as we update x in Krylov subspace, the residual will also converge to 0. The projection method seeks an approximate solution x m from an affine subspace of x 0 plus k m. We have discussed what is the definition of affine subspace in last few classes. By imposing the condition that b minus x m is perpendicular to L m, where L m is another subspace of dimension f and x 0 is the initial guess. In case of, so this is the statement for general projection method. In case of Krylov subspace methods, K m is given by K m of A r 0, where r 0 is b minus A x 0, and K m is a space spanned by r 0, A r 0, A square r 0 up to the power A to the power m minus 1 r 0. So, what we are thinking as multiple iterative steps or multiple search directions in a steepest descent algorithm is basically the multiple basis vectors through which x m is updated, x 0 is updated as x m, and these are the multiple several basis vectors of the Krylov subspace. And we have seen what is the grade of y with respect to A, what can be the maximum dimension of Krylov subspace, etc. in last few classes, and have shown that this is a convergent method. This in general Krylov subspace method should converge to the right solution based on any guess value of x 0 or any starting residual r 0. So, our goal is to develop efficient solvers using Krylov subspace method. The different versions of Krylov subspace methods arise from different choices of L m, that means the space on which to which the residual should be orthogonal, and from the way in which the system is preconditioned. This is a recapitulation slide of previous lectures. There are two broad choices for L m which gives best known techniques. One is L m is equal to K m, which is an orthogonal method, and another is L m is equal to A k m, which is an oblique projection. And now, in this particular session, we are concentrating on the full orthogonal method. We have earlier discussed about full orthogonal method also, and we will see how for symmetric matrix we can generate very efficient solver from full orthogonal method. And Arnoldi modified Gramschmidt is an algorithm through which we can get the basis vectors of this is basis vectors of V, the basis vectors of the Krylov subspace, which are the V's are the basis vectors of Krylov subspace. We can generate it through Arnoldi modified Gramschmidt method, that you start with any vector V1 and which is basically your when you are using full orthogonal method, this will be R 0, and then take a product of V with respect to the A matrix A V. From V you subtract A V. V is the basis of Krylov subspace, A V is the next basis of Krylov subspace. So, you orthogonalize V and A V using something like Gramschmidt method and find out the orthonormal basis vectors. In that way, you get another matrix which is Hij, which is the product between the new basis of Krylov subspace and the older basis of Krylov subspace before orthogonalization of the new basis. And this Hij forms a Hessenberg matrix Hm, and this Hessenberg matrix means, sorry, this is H bar m, forms a Hessenberg matrix H bar m. The Hessenberg matrix is basically an upper triangular matrix plus one subdiagonal term into it, and this is how we get Hj, because it goes up to Hj plus 1j. So, it goes up to the diagonal term and plus one subdiagonal term in it. Now, we look into the residual vector form Arnoldi's method. What is a residual vector at one particular iterative step on Arnoldi's method? And this is R m is equal to B minus A x m, and x m is x belongs to, so we have seen it earlier that x is equal to x 0, x m is equal to x 0 plus k m a y, and V m is orthonormal basis of k m. So, we can write x m is equal to x 0 plus V m multiplied by k m of x r 0 multiplied by y. So, x m is x 0 plus the Krylov subspace of A and R 0, and the orthonormal basis of this Krylov subspace is obtained as V m from Arnoldi's method. So, this comes from Arnoldi, from Arnoldi's method. So, you can write x m is equal to x 0 plus V m into y. So, you have substituted x m is equal to x 0 plus V m into y, V m into y m rather, and y m's are the coefficients which are multiplied with different basis vectors of Arnoldi's Krylov subspace to get a general expression of a general vector in Krylov subspace. So, x m is equal to x 0 plus a general vector in Krylov subspace, and we have to find out what y m is that, so that we can satisfy the equation, come to it later. So, this is B minus A x 0 plus V m y m, B minus A x 0 is equal to R 0. So, R 0 minus A V m y m, which is R 0 is again we have, if we go to the maybe to the previous slide. So, we started with not here, but if we not in the previous slide, if we see in full orthogonal method, right, in FOM, we started with the first basis of Krylov subspace is capital V is equal to mod of R 0 into V 1, and which I have written as beta into V 1. So, beta is mod of R 0, which is the first base magnitude of the error vector, first case of first residual in Krylov subspace, R 0 in Krylov subspace. So, beta V 1 is equal to, and we can write, and this is so we can write that V is equal to, or V is equal, rather we should not write that, we put R 0 is mod R 0 into V 1, V 1 is an unit basis, first basis vectors of the Krylov subspace, which is an unit vector. This is beta V 1. So, R 0 is equal to beta V 1, we substitute R 0 is equal to beta V 1, and the mth order residual is beta V 1 minus A V m y m. Now, from Arnoldi's method we got this identities. This comes again from Arnoldi. If we look into the Arnoldi's algorithm, which I have just shown in the last slide, these relations are evident from there, that A V m is equal to V m H m plus W m E m transpose, W m is H m plus 1 H m V m. So, now in A V m I will substitute A V m by this particular quantity. So, R m is equal to B veta 1 minus V m H m plus W m E m transpose Y m, and this is B veta 1 minus V m H m Y m minus H m plus 1 V m E m transpose. Now, what is Y m? And that is what we are trying to find out, what is the value of Y m, because if we know Y m, we have defined the Krylov subspace. Arnoldi's method will give us the orthonormal basis of Krylov subspace. If we can find Y m, we will multiply it with different basis vectors and find out what is the update in Krylov subspace, which has to be added with initial guess x 0, so that I get the final solution. So, now this update is obtained if we can remember steepest descent method. Alpha is the amount of distance that I should go along one particular direction vector r, and this is obtained from the relation that the residual is orthogonal to particular subspace. Similarly, full orthogonal method uses the fact that the residual is orthogonal to L m, which is same as K m. The residual is also orthogonal to the Krylov subspace only, and using that we can get. So, this is using the fact that full orthogonal method or Arnoldi's method for solving linear equation, that gives L m is equal to K m and R m is orthogonal to R m plus 1, rather is orthogonal to K m. So, using that we can find out, I have shown it in few lectures before, Y m is H m inverse beta E 1. So, H m Y m, H m is the Heisenberg matrix, the a part of the Heisenberg matrix which we have obtained in the last shown in the last slide. So, H m Y m is beta E 1, multiply both side by V m, V m H m Y m, which is this term is V m into beta y E 1. E 1 is an first unit vector 1 0 0, which is multiplied with V m will give the first vector in the of the orthonormal basis set beta V 1. So, I can write that this is equal to beta V 1 utilizing this factor, and they will cancel out. So, I will get that R m is minus H m plus 1 E m transpose Y m V m plus 1. This is a very important identity from the Arnoldi's method or from full orthogonal method, that the residual is orthogonal to the next basis in the Krylov subspace. Residual at one particular m level is orthogonal to the next basis function of Krylov subspace. Sorry, residual is not orthogonal, residual is parallel, the residual is along the next basis of Krylov subspace. So, residual will be orthogonal to the previous basis. I am sorry. Residual R m is along V m plus 1, where V m plus 1 is the m plus 1th basis of Krylov subspace. Mth residual is in the direction of m plus 1th basis of Krylov subspace. That is the finding. So, get R m is equal to minus H m plus 1 m E m transpose Y m V m plus 1. So, the residual vector is in the direction of V m plus 1, and residual vectors are orthogonal to each other. Why? This is simply due to the fact that V 1 is orthogonal to V 2 is V m is orthogonal to V m plus 1, which comes due to Arnoldi method is modified by Gramschmidt. Gramschmidt method will give a set of orthonormal vectors. So, these B vectors are orthogonal to each other. Therefore, once I see residual Rm is equal to something, say m Vm plus 1 and Rm minus 1 is equal to m minus 1 Vm, right. That is the founding here. Vm plus 1 and Vm are orthogonal to each other. So, Rm and Rm minus 1, that means Rm is orthogonal to Rm minus 1 and so on. So, residual vectors are orthogonal to each other. For a symmetric matrix A, Hm or the part of that Heisenberg matrix is a tridiagonal matrix. We have shown it earlier. If A becomes symmetric, Hm is a Heisenberg matrix. So, it has a it is a upper triangular matrix with one subdiagonal. If A is symmetric, so Hm is also symmetric. So, only the subdiagonal and superdiagonal exists and it becomes a tridiagonal matrix, and we can express this tridiagonal matrix as a product of two bidiagonal matrices. One is a lower triangular form, another is an upper triangular form. And if we use this form, these betas comes in terms of the H here. So, Rm becomes minus beta m plus 1 Em Ym Vm plus 1 for symmetric matrix A. If we can tridiagonalize the Heisenberg matrix Hm for symmetric matrix A, we can directly calculate from that form of the Heisenberg matrix, we can directly calculate what is the coefficient which will be multiplied with Em transpose Ym Vm plus 1 to get the residual vector. So, there is a relationship between the residual vector and the tridiagonal matrix which directly comes here. So, I will stop here in this session, and with this particular idea that our residual vectors are at mth level is along the base m plus 1th basis of Krylov subspace, and residual vectors are orthogonal to each other. We will see how this we got an expression for the residual vector for symmetric matrices, how this can be substituted into de Langs's algorithm or direct Langs's algorithm, where we are doing this TDMA type of calculation, and we can get a faster solution method. Thank you.